I want to do a few quick case studies, and then we'll be done. Okay? There's a few things that I think are interesting in the case study world. One is subdividing rings. Where do you take your sample? And here is laser ablation studies in true rings, and look at how many samples they got off of 2 different years with laser ablation. And what they found is that they stayed high, and then it dropped, and here it dropped pretty quickly. What is that related to? Well, this one had very little June precipitation. This one had a lot. So within the ring, I can tell you seasons, not just years, seasons with isotopes. Following me? And so that's pretty cool. This is some other work this is some of the work that came out of my lab with oxygen and redwoods. So we did 10 subdivisions of these are the tree ring boundaries for redwood trees, and we found a pretty consistent pattern. Is that a question or just a?
Yeah, it's a question. I'll wait till you're done.
Okay. Do I have to go back to the next slide, or is this one okay? Okay. So what we found was that the lowest point was in the middle of the ring. And what we're interpreting that to be, that is the most reasonable spring signature. And then after spring, they start to enrich because of warmer water sources and evaporative enrichment, and then they get to the ring boundary, and then they go back down. But here's my question to you. Why aren't they back down right away? Because these cells right here are made in the spring. Okay?
Well, if it's redwood, does it snow melt?
No. Okay, the reason is this. The cells that are made right here are not made with current photosynthate. They're made with photosynthate you made last year. You store it, and then you make your early tree rings with things that you have stored. So you have to be careful about this, right? So you have to say, so what's going on here is this is stored carbohydrate, but you also have current photosynthate, and you're starting to dilute the stored with current, and by the time you get down here, there's no more stored left. It's all gone. And all that is current photosynthate. Following me? So when we got this data, we said, okay, we want to sample 2 places on the ring. And I have undergraduates doing this, so I had to tell them, go to the middle of the ring. Cut out the middle of the ring right there. I don't care where it is, just cut out the middle. We call it middle wood because it's not early wood. Okay, it's not late. And I said, go to the ring boundary and cut out the ring boundary. And I don't even care if you get some from the next year. I want this part, this part, this, and I get 2 pieces of information that are very valuable. Now, why is that important? I want you to look at 2 years. Look at 2003. If I did the entire ring, integrate over the entire ring, I would get a value of about 27.7 per mil. Okay? Now, if I look at 2000, if I integrate that entire ring, I would get a value of about 27.7 per mil. So my isotope value would say 2000 is exactly the same as 2003. Are those years the same? Look at those 2 years. No way. So integration is fine up to a point. If you want to get seasonality stuff, you had better think about, where is your signal? If I want fog, which is a summer phenomenon, I really don't want to take the whole ring. You following me? Right? Okay. So subdividing. The other thing, this is another approach that's becoming pretty popular called the dual isotope approach. The dual isotope approach is this. I want to measure both carbon and oxygen on the same sample because I want to use one to constrain my interpretation of the other. Here's the deal. Carbon isotope variation is a function of supply and demand, stomatal conductance, and photosynthetic rate. But if I have a carbon isotope ratio, how do I know which one is which? Which one is more important? I can't tell which one is which. And so the idea is, let's use the oxygen isotopes because they might be responsive to stomatal conductance, but they're not responsive to photosynthesis. So oxygen isotope variation can be responsive to conductance, but not photosynthesis. So I use my oxygen isotope ratio to constrain my interpretation of the carbon isotope ratio. You following that? And so what they're doing is they're putting the carbon and the oxygen on these graphs, and these little arrows are, from treatment 1 to treatment 2 or site 1 or whatever your experiment is. However the arrow goes in this direction is interpreted as a change in photosynthesis and stomatal conductance in that direction. So they're using one to constrain the other. And this model has validity, it has good ideas, but there are a number of caveats that you have to be very careful about to apply this model. And there's some papers that I've written in 2012 that talk about things that you have to be careful about in order to make this model valid. And I don't want to go into them here, but just be aware that there's some interesting things going on in this regard. This is the last, near my last slides. This is some work by Brent Helliker showing this is grass. And what he used was the cellulose model that we developed for tree rings. And he used it on grass. But he had to be careful. He first started using this model, and he said, it doesn't work, John. Your model doesn't work. I said, well, why? Because he was getting wrong numbers. But he had to actually know, to parameterize it correctly, what leaf water is he going to use. And what's interesting about grass is, and Jim mentioned this, remember the string of lakes thing that he mentioned before? Well, look at that. This is the base of the leaf, -6, 7, 13, 20. In a single leaf, that's the variation within the leaf. That's the string of lakes right there. So he had to sort of average that, and where is the cellulose being made for the next leaf is in the column. And so if you actually parameterize it correctly, that's showing this graph, then you get a nice relationship. If you don't parameterize it correctly, you get wrong. So if you're going to use a non-tree ring kind of thing, you can still use the cellulose model, but you have to be careful about where everything is happening. Does it make sense? So you can be used on grasses. I think I'm going to skip this one a bit. This was a labeling study where they labeled with different humidities, isotopic labels, and they found different components, lipids, proteins, lignins, where they were going. They were tracing through the system. This one's a pretty cool one. What's going back paleoclimate records. This is wood from the Eocene. And not only I've never seen this happen before. They were look at what's going on in the Eocene, but they were subdividing. So they were looking at the seasonality in the Eocene, okay, with the tree rings, and going into some of that stuff. And they said their site was like 16 degrees warmer, and so found some good stuff. So fossil wood's cool.
How do these models compare with other reconstruction models, and do people have
other reconstruction models of cellulose?
Of using...
Oh, yeah, the temperatures in the Eocene stuff? I couldn't tell you I could look at the paper and look at what I'd have to go to their discussion section and look at what they compared it with. But I think it was ballpark. It's my recollection. Okay? All right. And finally, this is almost my last slide. We'll see if it is. In terms of carbon isotopes, there's two variations. Remember, supply and demand, and how do you tease those out? Well, with oxygen and hydrogen isotopes, there's also two things. Source water and evaporative enrichment. How can you tell which one is more important? So what people have wanted to find is, can I get an independent measure of source water out of the tree ring that has nothing to do with evaporation? And Leo Sternberg is doing this thing called glucose phenolosazone. I don't pronounce that correctly. And what he has found is that the second carbon on that molecule fully exchanges with water. 100% exchange. Okay? And so that molecule gives a slope of 1 to source water. So he's trying to get at source water. And by the way, I think someone asked, he also showed independently that the amount of exchange was 0.428%, or 42%. So that's an independent measure of what we talked about before. Another one, I think I blew this one up. This is another thing called lignin methoxy or methoxylignin. I think Todd's lab is doing some of that. Is that correct? Where's Roxy? They do. Okay. And the idea is to get at source water again, because this is precipitation and this is the methoxylignin, and there's a nice relationship. It's still some scatter and still some things maybe need to be worked out. But the idea is that people are trying to get at, can I get at one of these parameters and fix it so that I now know the other one and sort of get more information. Okay. Future directions. I'm not going to go into this much. I'm just going to show you what some people are doing. And here I give you all kinds of citations. If you ever wanted to look at fossil wood, here's a bunch of papers. Other isotope elements, nitrogen-15, strontium, calcium in tree rings. There you go. There's the papers. Other cellulose records, peat bogs, humidity reconstruction, air pollution studies. You want to do an air pollution study using tree rings? There they are. Go look at them. Shifts in precipitation patterns, monsoonal precipitation in either the Southwest or India or somewhere. Isotopomers, water sources, soil water, fog water utilization. Climate cycles like El Nino, hurricanes, solar activity, volcanic activity with tree rings have all been used. and isotopes in tree rings. Modeling geographic variation, physiological responses, archaeological studies, ecological interactions, annual growth trees without rings. This is the tropics. Remember the tropics? Mike Evans has done a lot of work with that. And then cross-dating using some tree rings. So there's a lot of things out there, and I've given you tons of citations if you ever want to interested in them. And that's that. I'm exactly at 10. I'm exactly at 10, but I've got a few more slides to show you some cool redwood stuff. If you guys are willing to stay for another 5 minutes. Can I give 5 minutes? Okay. Okay. So I'm going to talk to you about, this is just blowing my own horn. This is coming out of my lab. All right? This is what we've been doing. So redwoods. Jim told you how cool they were. They're using fog as a water source. As much as 40% of that water was derived from fog. But you know, Todd had that graph of 3 years. Do you remember that graph that showed the variation? And I saw that graph and I said, Todd, all 3 of those years are not the same. Why aren't they all the same? Well, he said, this year was a drought. This year was an El Nino event. And this year was average precip. I said, Todd, that is cool. If fog varies with those climate cycles, and that information goes into the tree ring, right? Now we could go very far back. And so that was the impetus. There's a couple things you need to do first, and I showed you this one. Where do you sample the ring? And also, is there coherence? I don't know if you can see these little red dots, but we had sites all along the Northern California coast. And this is the oxygen isotope variation. And there's coherence in signal from sites that are well over 500 kilometers apart. So there's a common environmental signal that all these sites are seeing, which is good stuff to use. Then we did 50-year correlations, 50 years of carbon isotopes with fog, sea surface temperature, the Pacific Decadal Oscillation. Do you all know what that is? It's like an El Nino event, but in the North Pacific. And Eureka Tmax. So now be careful. It's not surprising that these all correlate because these are all interrelated, aren't they? Sea surface temperature and PDO, and so they're all interrelated, so that's not surprising. But carbon isotopes are giving us good numbers. Oxygen isotopes of the middle wood, the stuff in the dead center of the ring, is telling us about February to April 500 HP geopotential height. High pressure systems, low pressure systems, right? High pressure systems, sunny, warm, low pressure, rainy, cold. So this is telling me about the spring conditions. The late wood is telling me about August to October. So I now have spring and late summer information about high pressure. I already showed you this one about fog and rain. So we got enough information that says, you know, these guys are recording climate. So NSF, give us some money because we want to go farther back. And they said, okay. And we needed to go and get slabs. Very large trees. This isn't a large one. This is a small one. So this tree is not huge big, but that's a 700-year-old tree. And we needed slabs because there's a lot of ring anomalies. And we talked about the wedging and things. When these trees get old, they get messy. Okay? But how do I get slabs? No one is going to let me cut down one of these trees. And I do not want to cut down one of these trees. Right? Beautiful organisms. I have the best field sites. Well, maybe not. Some people work in corals. But I have really cool field sites. Okay? But these trees fall down naturally in a windstorm. This is a tree that fell down in Prairie Creek Park 4 or 5 years ago. And you can see how big it was. And they had to clear this tree. It's covering the road. So if they clear the tree, there's an end of the tree that is available for sampling. And we have a permit to take the slab off of that tree. Now, for over 10 months of the year, you can't use a chainsaw in the state parks because there's a nesting bird that doesn't like it. Fair enough. I don't mind. But
It doesn't look like you were in the picture. Of course you don't mind.
I was using this. This is a 12-foot crosscut saw. They call them a misery whip. And I swear I have a lot of respect for old-time loggers. That's a hard. Anyway, we could cut them. And these trees don't look huge. This is not a huge tree, but that is a 1,700-year-old tree. And the oldest tree we have is 1,900 years old. We have about 10 slabs. If you can wait till the nesting period's over, you can get the Park Service to use their chainsaws and cut one for you. So here is an over 3-meter diameter tree, and that's a 6-foot bar on a chainsaw. And they cut these things for us, and then you take them back to your lab, and you have this big old slab put together. Anyway, that's just the fun part. But here's some cool data. This is a very good point. Let me back up at least one. Here, we're not getting the base of the tree. It's wherever they fell. I don't want the base of the tree. I really don't. You want to know why? I don't know if how many have ever been to the old growth redwood forest? Oh, shoot, you got to go. If you haven't, there's a lot of burn. Have you ever seen those cavities that are burned out? And also, the ring anomalies get really bad. The bark gets really odd-shaped. I want my core about 10 to 20 meters up. I mean, my slab. It's more circular. See how circular that is? There's not a lot of anomalies. The number of rings, I'll lose some. I'll lose some. But I got 1,700, you know. Okay, I will lose some.
What's yours? The similarity when we doing the C14 for the aging, because it's similar wood.
Yep. You're doing C14 aging?
Yes.
Yeah. It wouldn't matter for the C14 where on the tree you're doing.
It's like where we have to put the samples.
The increment core? Is it an increment core?
Yeah.
You can take it wherever, breast height. You take it wherever you are. It doesn't matter. It won't matter. Not for carbon 14. Anyway, so PDO. This is the recorded PDO, and this is our correlation, and it's a fairly good one. This is a 1,000-year reconstruction of the PDO. Okay, using the tree rings, and we always think PDO is about a 30-year cycle, and it seems to be. Why is this valuable? Because this is a baseline. This is a baseline, and this is not the only record. There are 3, and we're starting to compare all the different other kind of records, some speleotherms and other things. But you know, once we get enough of these, we'll have a good baseline of what the PDO is, and then what's going to change in the near future? What might change with the PDO in the near future? How do you know that with something of a 30-year cycle, and you only have maybe 100 years of records, how do you know what is normal? You really don't. You need a longer-term strategy. Tree rings, some of you who are geologists might say, tree rings, they only go back 2,000, 3,000, 4,000 years, right? They're only really covering the Holocene. You know, but let's think about this in terms of us. The whole, you know, going back prior to the Industrial Revolution to now is really important data for what humans are doing, what anthropogenic changes, and going back 1,000 years and having this kind of what's the baseline in the Holocene comparing to what we're doing to the planet. This is really the important time frames. It's great to go back 1,000,000 years, but this is really, if you're looking at human anthropogenic climate change, is the most important period to look at. So even though tree rings don't go far back, they go into a very important component of our world. Finally, this is drought. 2014 and 15, California had a major drought. How many heard of that? Was it unusual? How do you know? Well, we now know that in the last 1,000 years they've had at least 14 droughts of similar nature in California, in Northern California at least. So yes, it's not an every 10-year event. It might be every 100-year event. It was bad, but it wasn't like outrageously unusual. And this is some more information about extreme events. Extreme wet, extreme dry during the medieval warm period, the Little Ice Age, and the current warming. How are those things changing? Again, you can start to think of all you can do with a 1,000-year record and this stuff. And I'm going into Jed's time, so I'm going to stop. And thank you for your attention.